Now, I will try to drive the four-dimensional equation of motion for a free charge particle without interacting with the electric and magnetic field. Then I will add up the Lagrangian to the interaction, and I'll try to find the four-dimensional Lorentz force. So here is the Lagrangian we have, which depends on the derivatives with respect to the proper length. And here is the Euler Lagrange equation. So let us try to calculate d over ds del over del of dx, let's say instead of alpha different indices, gamma over ds of our Lagrangian is minus mc g alpha beta dx alpha over ds dx beta over ds have to be taken. Have to be equal to 0 because there is no any dependence of the Lagrangian with the coordinates. The Lagrangian depends on the derivative of the coordinates. So let me show you how we are going to take this derivative and how we find the equation of motion. So basically this is equal to d over ds. So if you take the derivative of dx gamma over ds, one of the terms, let's say dx alpha over ds, what we are going to obtain? We have minus mc. So the exponent of the square root of 2 will bring 1 over 2. So when gamma and alpha equal to each other, you can take the derivative, otherwise you cannot take the derivative. So that could be represented by a conical delta. Okay, so conical delta of gamma and alpha. So alpha is in the down in this here, and here this is the up in this, upstairs. Gamma is the upstairs index and alpha is the downstairs index. So then if you take the derivative with respect to dx alpha over ds, what is the leftover terms? That is g alpha beta dx beta over ds. Then you have to subtract 1 from the exponent of the square root of, that will be minus 1 over 2, then this term will be g alpha beta dx alpha over ds dx beta over ds. So this is the derivative of the first term. So then you can look at what is the free index. Beta is contracted and alpha is contracted, and free index is gamma. So this indices are in the correct places, and if you contract the alphas and betas, you have the free index gamma. What is the next derivative? This is the derivative with respect to the alpha. What is the next derivative? What is the next derivative? I take the derivative with respect to the dx alpha over ds. The next will be the derivative with respect to the beta, dx beta over ds. So therefore, for the additional term will be the following: plus, if you take the derivative with respect to the beta, again you will have the exponent of the square root of the 1 over 2. Then you will have conical delta of what? Gamma and beta, g alpha beta dx alpha over ds times 1 over g alpha beta dx alpha over ds dx beta over ds, and this whole term have to be 0. So let us do it again. If you take the derivative dx alpha over ds with respect to this term, then the leftover term coefficients are the g alpha beta dx alpha over ds. From the derivative you have 1 over 2. When alpha is not equal to beta, that is equal to 0, otherwise you will have the free index of alpha. So basically this calculation is the following: d over ds minus mc and let us contract and see the free indexes again. Beta and alpha will contract and will yield the index as what? Gamma. And here beta and alpha will be contract and the free index will be gamma. So basically this will be dx gamma over ds times these leftover terms are the same, that is equal to 1 over square root of g alpha beta dx alpha over ds dx beta over ds, and that have to be equal to 0. So did you understand how we did the derivative operations? It is simple. We are taking we have two velocities, think about this, and we have to take the velocity here, derivative with respect to the velocity. First we are taking the derivative with respect to this term, then we are taking the derivative with the other term. And when the gamma and alpha is different, that is 0. And for the other derivative, when the gamma and beta indices are different, that is 0, and you can express this by the conical deltas. That is simple. And the only thing you have to look at what would be the free index. Free index should be gamma, and here in all representations free index is gamma. Beta and beta is contracted, alpha is contracted, and what will be the free index? Gamma, and gamma is in the upstairs. And here again beta and beta is contracted, alpha is contracted, free index is gamma, and gamma is upstairs in both cases. And these two terms are the same after the contraction. And on the leftover term, here you have excess term, but you can handle that excess term very easily. What is this excess term in the square root of 2? G alpha beta dx alpha beta ds. Look at here, which term? So instead of this, you can write c d tau over ds. Okay? Instead of this term, you can write c d tau over ds. So if you do this, things are more simple. So this term is c d tau over ds. So basically derivative is now taken with respect to the d tau, because this ds and this ds is cancel out, c's cancel, and this is the dx gamma over d tau. And look at here, instead of ds, what you can write? Instead of ds, now you can write c d tau over this stuff. So that means that what? Instead of ds, you can write c d tau over square root of g alpha beta dx alpha over ds dx beta over ds. This is non-zero. Left hand side is 0, that will be cancelled, and all the terms turns to be what? D over d tau times m dx gamma over d tau have to be equal to 0. That means that m times d square over d tau square x alpha x gamma have to be 0. Okay? So for that term, ds will be cancelled. This will be derivative of the 4 vector with respect to the proper time. And for the ds, you can write c times d tau over this. And this whole is non-zero. Therefore, this turns to be d over d tau. So therefore, you have a second degree of the derivative of the 4 vector, space-time vector with respect to the proper time. And this is the equation of motion of the what? 4-dimensional equation of motion of the free charge without interacting electric and magnetic field. So time coordinate is ct. If you take the double derivative with respect to the tau, that will be 0, and the space coordinates is the xyz, and that will be the ordinary second derivatives of the derivatives of the what space coordinates. So this is the covariant form of the extensively manifestly covariant form of the free Lagrangian. This is the earlier Lagrange equations, and if you apply the earlier Lagrange equations, we find the 4-dimensional equation of motion of the relativistic charge. 0 corresponds to ct, time coordinate, and the 1, 2, 3 represents the what? Space coordinate of the charge, and this is taken with respect to the second derivative with respect to the proper time. Now the next thing, how we can include the interaction term. How we can include this interaction term to the Lagrangian. So let us look at the action again. Let us look at the action again. We have an action if we have no interaction with the electric and magnetic field, that is equal to from S1 to S2 proper length interval of mg g alpha beta dx alpha over ds dx beta over ds, and so let me take the minus parenthesis here, integrate it through the ds. And if you look at here nicely, you are seeing that instead of ds, if you write d tau, nothing will be changed. You will change the integration limits. So what is the other Lorentz invariant quantity which we use as an interaction term when we derived the Lagrangian for the relativistic charge particle in an elementary way? That was the scalar product of what? U alpha, A alpha. That was an invariant quantity. So basically, you can adopt this term here in the following form: E over C. So E over C with minus sign. Therefore, you can put it as a positive. And you can write this derivative with respect to the proper length instead of proper time. times A alpha. Maybe let me write as a beta. So this term is the interaction term. This is the scalar product of the 4 velocity with the 4 potential, like we did in the elementary approach. So, but if you look at here, ds and ds, that could be replaced by the tau. Okay, you can take the integral with respect to tau also. So that term is the interaction term, and we know that this is invariant because this is a scalar product. This is invariant in all inertial frames, and ds is invariant in all frames. This action is invariant. Okay, no problem with that. Now let us try to find the equation of motion. Equation of motion. So I will call this as a negative of L tilde. L tilde is the new Lagrangian, which is interacting with the charges interacting with the electric and magnetic field. And now, if you write the equation of motion, then you will have the following: del d over ds, del L tilde over del what are the velocities here in this Lagrangian? Again, the velocities, what are the velocities? Dx alpha over ds, dx beta over ds, dx beta over ds are the velocities. So we have to take the derivative of the Lagrangian with respect to the velocities seen there. So let me decouple here and erase this part. And that is d over dx alpha over ds minus then the derivative of the Lagrangian with respect to the coordinates. So the coordinates are del Lagrangian over these four potential depends on the for coordinates. So you can write this as a del over del x alpha is equal to 0, or you can express this as a del alpha del tilde. They are the same presentation. So in that case, the Lagrangian has dependence of the velocities, the change of the four space-time with respect to the proper length, and x is depending on the vector potential is depending on the four potential is depending on the space and time coordinates. So now this is the earlier Lagrange equation, and let us find the equation of motion. So let me first calculate this one, del alpha over L tilde, or del L tilde over del x alpha. So that is equal to del alpha acting to the L tilde, del L tilde over del x alpha so these are the velocities only that will act to the for potential, and that derivative will be what? E over C dx beta over ds del A beta over del x alpha. So let me take this to the up. So only coordinates of the space-time, only for potential is the dependence of the space and time. So this presentation and that presentation are the same, and therefore we have to take the derivative with respect to the we have to take the vector derivative of the vector potential with respect to the coordinates of the space of time, and that could be expressed as E over C dx beta over ds del alpha A beta. So one of the p's in the earlier Lagrange equation, this part we will use. Now let us try to evaluate the derivative of the Lagrangian with respect to the velocity is there. So del L tilde over del dx alpha over ds I have to calculate. I already calculated the first derivative, first part, and the first part is equal to mc dx alpha. In the previous case that was dx gamma, and that was equal to c terms will be cancelled, so there is no c. That is equal to d tau. So we already calculated this, and for the second part, if you take the derivative of the velocity of the second part of the Lagrangian, you will end up with what? E over C A alpha. So you will take the derivative with respect to that term. Basically here beta in the index. So if you take the derivative with respect to alpha, you will have the chronicle delta alpha beta, and if you contract through the beta, the free index will be the alpha. So let me put these things to the earlier Lagrange equations. So I calculated the first term in the previous application. For the other term, if you take the dx alpha over ds with respect to the dx beta over ds, that will be chronicle delta alpha beta, beta is down, and times the a beta, and if you contract through the beta indices as a free, contract through the beta indices, free index will be the alpha. Now go one more step. So then plug this information and take the derivative of that with respect to the d over ds, and that will be the following: d over ds of this term, that is m dx alpha over d tau plus E over C A alpha d over ds of this term in here. minus del alpha over Lagrangian, and it is evaluated there, that is equal to minus E over C dx beta over ds del alpha A beta have to be equal to 0. So let us do the same trick we did earlier. Instead of ds, you can say c d tau over square root of g alpha beta and other velocities. So ds could be written as c d tau divided by g alpha beta dx alpha over ds dx beta over ds, and you can do the same thing here, that is c d tau over square root of g alpha beta dx alpha over ds dx beta over ds. So these are non-zero, that will be cancelled, c will be cancelled, and you can convert the derivative with respect to the d tau instead of with respect to the ds. And if you do this, you are obtaining the following. The first derivative, d over d tau times m dx alpha over d tau, and the other term plus e over c a alpha minus e over c dx beta over d tau times del alpha a beta is equal to 0. So we are coming to the end. So basically the situation is the following. If you take the derivative of the d tau, you will obtain the following: m d square x alpha over d tau square. For the term d over d tau a alpha e over c you have, minus e over c dx beta over d tau del alpha a beta have to be 0. For this term, you can write the following. You can use the chain rule, dx beta over d tau dx beta over a alpha. So you can call this expression as a del beta a alpha. So basically that turns to be the following form: m d square x alpha over d tau. So if you take the things to the other side, this goes positive, this goes as a negative. In the e over c parenthesis, what you are going to obtain? You will obtain del alpha a beta if you take this to the other side. And if you take this to the other side, that will be minus del beta a alpha, and multiplied with dx beta over d tau. So let us rewrite this expression. So this we find something we know. So I am not erasing this part. Let me write this again. M d square x alpha over d tau square is equal to E over C. Do you remember what is this? What is this? Del alpha A beta minus del beta A alpha. That is the Maxwell field strength tensor. So that is equal to F alpha beta. And do you remember what could be this? That is the derivative of the 4 vector with respect to the proper time. What is this? That is nothing but U beta and U beta. Proper 4 velocity. And what is this equation? This is the 4-dimensional Lorentz force. Okay, so that means that this Lagrangian is working well, and we can find that the covariant form, this is the covariant form of the 4-dimensional Lorentz force. Okay, using this you can find that the Hamiltonian also, Hamiltonian equation of motions also. So you are not familiar with this kind of calculation, so I advise to go and do all your calculations step by step, okay, by your own. So then you will understand what is going on. So you have to take the derivatives, indices, and you have to arrange the indices correctly. And so do this exercise by yourself again. So next time I will study that the motion of the charged particle in the electric and magnetic field first. Then I will define that the Lagrangian density instead of Lagrangian in order to find the equation of motion of the electric and magnetic field. Equation of motion of the electric and magnetic field will be the Maxwell's equations. Okay, so we now derived that the covariant form of the charged particle, Lagrangian for a charged particle is moving with the under the influence of the electric and magnetic field. That Lagrangian is correct. ds is everywhere is the ds, proper length. This is invariant. Our equations are in what should be action is invariant. Therefore, the earlier Lagrange equation coming from that the variation of the action should be covariant. Indeed, we find that eventually the covariant form of the 4-dimensional Lorentz force. Okay, so for today that's enough.